Welcome again. We are studying our second chapter, Calculus on Scalar Fields. Today we are going to start our 8th module. Its title is Sufficient Conditions of Differentiability. Earlier, we have introduced the notions of differentiability and total derivative for a scalar field at a point of its domain. But we have seen that using this definition, it is a little bit tough to check whether a function is differentiable at a point or not. Today, we shall study some results which will be more workable than the definition. Let us start with mentioning the learning objectives. First, we shall study two sets of sufficient conditions for differentiability of a scalar field, and then we shall go through examples citing how to use the above conditions. Let us start this module by recalling mean value theorem for vector derivatives of scalar fields. The statement is as follows: let A be a subset of Rn, F is a scalar field defined on the set A and A be an interior point of the set A. We further assume that we have such a vector y in Rn such that for all t from the bounded closed interval 0 to 1, the vector derivative f dash a plus ty y exists. Then there exists at least one theta lying in the open interval 0 to 1 such that we can express the increment f of a plus y minus f a equal to the vector derivative f dash a plus theta y y. Today we shall give a generalized version of this result. Let A be a subset of Rn, F is a scalar field defined on the set R and A is an interior point of the set A. We assume that for some vector y in Rn and for each t belonging to the bounded closed interval alpha beta, the vector derivatives f dash a plus ty y exist. We take alpha less than beta so that the interval is non-degenerate, that is, it is not a singleton set. Then there exists a gamma in the open interval alpha to beta such that we can express f of a plus beta y minus f of alpha a plus alpha y equal to beta minus alpha times the vector derivative f dash a plus gamma y y. Let us give the proof. We define a function g from closed interval alpha beta to R by g t equal to f of a plus t y for each t in the closed interval alpha beta. So, g takes some t from alpha beta first to the vector a plus t y, which is a member in the set A, and then f takes it to R. So, g is well defined and it is real valued. Now, we know for every t belonging to alpha beta, we have g dash t equal to the vector derivative f dash a plus t y y. That is, for every t in the closed interval alpha beta, g dash t exists. Thus, the function g is differentiable and continuous over the bounded closed interval alpha beta, so that we can apply Lagrange's mean value theorem for this function for this particular interval. By the theorem, there exists a gamma from the open interval alpha beta such that we can express g beta minus g alpha equal to beta minus alpha times g dash gamma, that is, f of a plus beta y minus f of a plus alpha y equal to beta minus alpha times vector derivative f dash a plus gamma y y. So, the proof is complete. Now, we consider a particular case of this result. Let A be a subset of R, F is a map from A to R. So, we are considering a real valued function of a single real variable. We assume that F is differentiable for each t in the bounded closed interval alpha beta which lies in the set A. Then from the above result we put in particular A equal to 0 and y equal to 1. So, we have f beta minus f alpha equal to beta minus alpha vector derivative f dash gamma 1. We know f dash gamma 1 is nothing but the operator f dash gamma acting over 1, and that is nothing but the real number f dash gamma. So, we have f beta minus f alpha equal to beta minus alpha times f dash gamma, where gamma is a point lying in between alpha and beta, leaving the two endpoints. This is our known Lagrange's mean value theorem of single variable calculus. We have already seen that if a scalar field f is differentiable at a point A, then all the partial derivatives of f exist at that point. However, the converse of this result is not true. We have cited this by some examples. So, naturally arises the question, if some more conditions are added with the existence of all possible partial derivatives of f and A, will it imply differentiability of f at the point A? In the following result, we give an affirmative answer. We are going to discuss sufficient conditions for differentiability. Our strategy will be the following. We have to write the increment of f, say f of a plus y minus f a, as sum of two things. First one is the linear transformation f dash a operating on y, then the second term, that is norm y E f a y. Now, we can make the first term simpler by writing f dash a y equal to inner product grad f a and y. So, we have to take care of the second term in the right hand side. So, if we consider the quantity f of a plus y minus f a minus inner product grad f a y, whether we can express this as norm y times something, and this something should tend to 0 as y approaches origin. This will be our strategy. We start with our first theorem. Let A be a subset of Rn, f is a scalar field defined on the set A, and A is an interior point of the set A. We assume that all the partial derivatives of the scalar field f exist in some open sphere SAR subset of Rn and are continuous at the point A, then f is differentiable at the point A. Let us recall, by the symbol SAR, we mean the open sphere with center at A and radius r. So, here in addition to the existence of all the partial derivatives of f at the point A, we assume the existence of partial derivatives in some open sphere with center at A and then continuity of them at that point A. Let us start the proof. In order to prove the given hypothesis, we are to find and prove the existence of a linear transformation T from Rn to R such that for every y in Rn such that a plus y is in SAR, we can express the increment f of a plus y minus f a equal to T y plus norm y E a y, where E a y tends to 0 as y approaches the origin. We recall that the above equation is called the first order Taylor formula. first we have to guess what will be my t. From our earlier knowledge, we know that if such a linear transformation exists, then its matrix representation with respect to the standard frames of R n and R will be the 1 by n matrix consisting of all the partial derivatives of A at the point A in their natural order, and hence gradient of f at the point A is the n vector whose components are del f del x 1 A up to del f del x n A. Moreover, in such a case, for every y in R n, we must have T y equal to inner product of grad f A and y. Now, if y equal to the null vector, then there remains nothing to prove, because if we look at the left hand side, it is t theta. We know any linear transformation carries the 0 vector to the 0 vector. So, the left hand side is 0, and if in the right hand side we put y equal to theta, then it must be 0. So, both the sides of the first order Taylor formula vanish in this case. So, now let y different from the null vector. Let us put y equal to h v, where v is a non-zero vector. Now, we can uniquely express v equal to v 1 e 1 plus v 2 e 2 plus v n e n, where e 1 up to e n denotes the standard unit coordinate frame on R n, that is E I has the ith coordinate 1 and all other 0. Now, we consider the following collection of n many vectors, n plus 1 many vectors. U 0 is the 0 vector, U 1 is V 1 U 1, U 2 is V 1 U 1 plus V 2 E 2, that is it is U 1 plus V 2 E 2. Going in this manner, the last one U n equal to V 1 E 1 plus V 2 E 2 plus up to V n E n, that is U n is U n minus 1 plus V n E n. So, that is U 1 minus U 0 equal to V 1 E 1, U 2 minus U 1 equals V 2 E 2, and similarly U n minus U n minus 1 equal to V n E n. In language, the difference between two consecutive vectors is a multiple of a coordinate vector, that is, it must be parallel to a coordinate axis. With the help of this picture, let us illustrate the case for R 3. U 0 is the 0 vector, that is the origin. Next, U 1 is the vector whose initial point is the origin and terminal point is x 1 0 0. So, obviously, it is parallel to x 1 axis. The next one is the vector starting from x 1 0 0 to x 1 x 2 0, that is it is parallel to x 2 axis. The next one, it starts from x 1 x 2 0 and goes up to x 1 x 2 x 3. So, it is parallel to the x 3 axis, and in this case y is the vector starting from the origin to the point x 1 x 2 x 3. So, we can express f of a plus y minus f a equals to f of a plus h v minus f a. So, we write v in its elaborate form, then we can write this in this manner: f a plus h v 1 e 1 minus f a plus f of a plus h v 1 e 1 plus h v 2 e 2 minus f of a plus h v 1 e 1, and continues up to the term f of a plus h v 1 e 1 plus h v 2 e 2 up to h v n e n minus f of a plus h v 1 e 1 plus up to h v n minus 1 e n minus 1. To make our computations easier, we write b 0 equal to a, b 1 equal to a plus h v 1 e 1, and b n minus 1 equal to a plus h v 1 e 1 plus h v 2 e 2 up to h v n minus 1 a n minus 1. So, f of a plus y minus f a equals to f of b 0 plus h v 1 e 1 minus f b 0 plus f of b 1 plus h v 2 e 2 minus f b 1 and so on. If we look at this term carefully, we can find that in any bracket the second term takes care of the first term of the previous bracket. Now, we are going to use the mean value theorem for vector derivatives of scalar fields. In this case, it is f for each member in the right hand side. So, we have f of a plus y minus f a equal to h v 1 del f del x 1 at c 1 plus h v 2 del f del x 2 at c 2 plus up to h v n del f del x n at c n, where for each possible I, c I is a point in the line segment joining the points b I minus 1 and b I, but c I must be different from the points b I minus 1 and b I which lie at the end. Now, if y lies inside the open sphere SAR, then by definition of open sphere we must have norm of y minus a less than r. Then obviously, norm of b I minus a less than r for each I. Since c I lies on the line segment joining b i's and b I plus 1's, we have norm of c I minus a less than r. So, c I are also in the open sphere SAR, and hence the partial derivatives del f del x I exist at the point c I for each I. On the other hand, let us calculate the inner product grad f a and y. So, we have grad f a inner product with h times v 1 e 1 plus v 2 e 2 plus up to v n e n. Since inner product is homogeneous, we can take the scalar h outside. So, we have h inner product grad f a and v. So, we write them in elaborate form, and then putting the value we have h times del f del x 1 at a v 1 plus up to del f del x n at a multiplied by v n. Combining the above two relations, we find that f of a plus y minus f a minus inner product grad f a and y equals with, after some calculations, h times summation v I del f del x I at c I minus del f del x I at a, where summation runs over from 1 to n. Now, if y tends to the origin, then v tends to the origin. Therefore, the n-tuple v 1, v 2, v n tends to 0, 0, 0, 0, that is v I tends to 0 for each I. So, b I plus h v I e I tends to b I, and hence c I tends to a for each I, that is del f del x I at c I tends to del f del x I at a, because of the continuity of del f del x I at a, and this implies h times summation v I del f del x I at c I minus del f del x I at a tends to 0. Let us denote E A y equal to h by norm h summation I equal to 1 to n v I del f del x I at c I minus del f del x I at a for y not equal to theta. As h is a real number, norm h is nothing but modulus h. So, modulus of E A, it is obviously non-negative and equals with modulus of inner product V w divided by norm V, where w is the vector del f del x I c minus del f del x I a, I runs from 1 to n. Clearly, when y approaches origin, w also. Then we find that modulus of E A y less than mod w and it tends to 0 as y tends to theta. So, that is in the first order Taylor formula the error term tends to 0 and hence the scalar field f is differentiable at the point A. So, our result is proved. In the above proof, we resolved the vector y into n many parts, and our intention was that we have to use the relation the linear operator f dash a operating on z equal to the vector derivative f dash a z for each part z. And also we selected all these parts parallel to the coordinate axis, that is those vectors were scalar multiples of the vectors E I. We use this because we wanted to use the relation vector derivative f dash a E I equal to del f del x I at the point A. If we look at the statement, we were provided information regarding the partial derivatives and our target was to prove the existence of f dash a. Another result for sufficient conditions for differentiability is the following theorem. Let A be a subset of Rn, f is a scalar field defined on the set A and A is an interior point of the set A. We assume that one of the partial derivatives of f exists at the point A and the remaining n minus 1 partial derivatives exist in some open sphere SAR and are continuous at A. Then the scalar field f is differentiable at the point A. We give the proof, it is similar to the earlier one. Without loss of generality, we can assume that del f del x1 exists at A and the remaining n minus 1 partial derivatives del f del x2 up to del f del xn exist in some open sphere SAR and are continuous at that point A. This means that for every suitable y, we are to prove f of a plus y minus f a equal to inner product grad f a y added with norm y E a y, where E a y should approach 0 as y goes to origin. Let y equal to h v. Here v is the unit vector in the direction of y. We did not assume that in our earlier proof. So, in this case we have h equal to norm of y. Now, we can uniquely express v equal to v1 e1 plus v2 e2 up to vn en, where e1 to en denotes the standard unit coordinate frame on Rn. Hence, like the previous case, we can write f of a plus y minus f a equal to f of a plus h u n minus f of a plus h u n minus 1 up to f of a plus h u 1 minus f of a plus h u 0, where u 0 is the origin, u 1 is v 1 e 1, u 2 is v 1 e 1 plus v 2 e 2 up to u n equal to v 1 e 1 plus up to v n e n. Now, the vectors a plus h u 0 equal to a and a plus h u 1, which is nothing but a plus h v 1 e 1, differ only in their component along the x 1 axis. Since del f del x 1 exists at the point A, we can write f of a plus h u 1 minus f of a plus h u 0 equal to h v 1 del f del x 1 at A plus h v 1 p 1, where h tends to 0 implies p 1 tends to 0. We explained it here. If we take the limit of f of a plus h u 1 minus f a by h as h approaches 0, we have the limit exists and is equal to v 1 del f del x 1 at A. So, that is why f of a plus h u 1 minus f of a plus h u 0 must be h times v 1 del f del x 1 at A plus some error terms. Now, for every I from 1 to n, we write f of a plus h u I minus 1 plus h v I e I minus f of a plus h u I minus 1 equal to f of b I plus h v I minus f of b I, where b I is a plus h u I minus 1. Then these 2 points b I and b I plus h v I e I differ only along the ith coordinate axis. Now, we apply Lagrange's mean value theorem, and hence we find f on b I plus h v I e I minus f b I equal to h v I del f del x I at C I, where C I lies on the line segment joining b I and b I plus h v I e I. Clearly, when v tends to origin, h tends to 0, and consequently the point C I tends to A. As for each running from I equal to 2 to n, we repeat to give stress I equal to 2 to n. The scalar field del f del x I is continuous at A. We can write del f del x I at C I minus del f del x I at A, which is nothing but P I goes to 0 as C I tends to A. Combining all the above relations, we can express f of a plus y minus f a equal to nothing but h times inner product grad f a and v plus h times v n p n plus up to v 1 p 1. So, we write this as inner product grad f a and y plus norm y e, here equal to v n p n plus up to v 1 p 1. So, it depends on v i's and p i's, and we have already seen that as y tends to theta, p I tends to 0. So, y tends to theta implies E also tends to 0. So, this completes the proof. So, we have studied two different set of sufficient conditions for differentiability. Now, we are going to cite some examples in which we shall apply the previous two results. Now, we cite some examples. First one, let us consider the scalar field f defined on R n by for every x in R n f x equal to inner product x x, that is norm x square. So, if x equal to x 1 x 2 up to x n, we find that f x is nothing but x 1 square plus x 2 square plus up to x n square. So, we consider some arbitrary but fixed point a equal to a 1 to a n in R n. We can easily check del f del x 1 at a equal to 2 a 1, del f del x n at a equal to 2 a n. Moreover, if I consider the point A for any open sphere with center at A, we can find that all the partial derivatives exist and all of them are continuous at the point A. As a result, f is differentiable at A. Moreover, grad f at A equal to twice A. Now, this result can also be calculated if we start from the very definition. We show it here also. We take any h in R n, then obviously at the point a plus h, f is well defined. We find that f of a plus h minus f a equal to inner product a plus h minus inner product a. In the first term of the right hand side, if we apply the additivity property of inner product, it will give me 4 terms. The first term will be inner product a, which will be vanished whenever we add it with the last term given. So, we finally have twice inner product a h plus inner product h h. Here, if we consider the map T from R n to R defined by any h in R n goes to inner product a h, it is a linear transformation, and moreover norm h square, that is inner product h h, goes to 0 as h tends to origin faster than norm h. As a result, f is differentiable at the point A. Another example. Let us define the sum of coordinate functions s from Rn to R and product of coordinates functions p from Rn to R as follows. We take any point x equal to x1 up to xn in Rn. So, the sum function will be sum of coordinates of x, that is Sx will be x1 plus x2 plus up to xn, and Px will give us the product of all the components of the vector x, that is x1 into x2 up to xn. We select some point A equal to a1 up to an in Rn. We can easily check that del s del x1 at A is 1, del s del xn at A is 1. So, for the scalar field S, all the partial derivatives exist in some open sphere with center at A, as well as all of them are continuous at the point A. So, S is differentiable at the point A. Similar things happen whenever we consider the scalar field P also. Here we can find del P del x1 at A equal to A2 into An, and going in the like manner del P del xn at A equal to A1 up to An minus 1, all exist in any open sphere SAR and also continuous at A. Clearly here grad S at the point A equal to 1 1 1 1 1 and grad P at the point A equals to theta if at least one AI vanishes, otherwise it is B1, B2 up to Bn, where B1 is PA by A1, B2 equal to PA by A2 and so on, Bn equal to PA by An. So, we have studied two different set of sufficient conditions for differentiability and did some examples to see how to use them. With this module comes to an end.